Hello, so in this video we will talk about the comparison between arithmetic mean and the geometric mean of a set of positive real numbers. So for this end, let's define the notation. So we'll say that arithmetic mean 1 to n, this is equal to some set of numbers like that. So it's a sum of n positive real numbers divided by the number of numbers. And we'll define geometric mean from 1 to n. This is equal to the product of them, same numbers, and we take the nth root. So now our job is to prove that arithmetic mean of n numbers is always greater than or equal to the geometric means of those same n numbers. Okay, so the technique we will use is mathematical induction. So what are the two steps of mathematical inductions? We have a base step and we have an inductive step. So for base step, we have n is equal to 2. So in other words, what we want to say is a 1 to 2 is always greater than or equal to g 1 to 2. In other words, if we expand this, we want to say that a1 plus a2 divided by 2 is greater than or equal to root of a1 a2. So this is what we want to prove. Okay, now I can take this 2 on the other side. So a1 plus a2 is greater than a1 a2. I put a question mark because we have not proved it yet. Okay, sorry, 2 here. And then we can bring this 2 times root a1 a2 on the other side. So we can say a1 plus a2 minus 2 times a1 a2 greater than 0. Okay, now this is what? This is nothing but root a1 minus root a2 squared. Now since this is a square and square is always positive, so then this is actually now proved. So now we come to the inductive step. Okay, now inductive step is a little bit involved, and that is where the Cauchy's method is very smart. So what he did was he split the inductive step into two cases. One is when n is a power of 2 and the other is n is not a power of 2. Okay, so we'll say case 1 here. We'll just say first of all n is equal to some 2 to the m, let's say. Okay, and then we will play our induction on this m. Okay, so let's say that so assume in inductive step, what do? We assume that a1 to 2 to the m, this is greater than g1 to 2 to the m. Okay, and we have to prove that a1 to 2 to the m plus 1, this is greater than g1 to 2 to the m plus 1. Okay, so now we will prove it by mathematical induction. Okay, so let's say, what is this guy? So this guy is a1 plus a2 plus a to the 2 m plus 1 divided by 2m plus 1. Now since we have 2 to the m, so since use 2 to the m is equal to n. Okay, so we can just say a1 plus a2 plus a2n divided by 2n. Why? Because if 2 to the m is n, then 2 to the m plus 1, this is equal to 2 to the m times 2, which is equal to n times 2, which is equal to 2n. Okay, so this was straightforward. Okay, now this guy we can split more. So we can say that a1 plus a2 plus up to n over n plus the next n numbers. So we start with n plus 1 and then end with n. But there's a 2 also in the denominator. So what we do? We say this divided by 2. Okay. Now consider this guy, this whole term as one number and this whole thing as another number. So this way I can say the first is arithmetic mean of 1 to n. The second guy is arithmetic mean of n plus 1 to 2n. And the overall thing is arithmetic mean of these two numbers, because we are adding these two numbers and dividing by 2. Okay. Now, what did we assume in the start? That the n numbers arithmetic mean is greater than those n numbers geometric mean. So then this means that this guy is greater than arithmetic mean of geometric mean of 1 to n and geometric mean of n plus 1 to 2n. And what does our base step say? Our base step says that if we have two numbers and their arithmetic mean is greater than their geometric mean, so then this guy is greater than geometric mean of 1 to n and geometric mean of n plus 1 to 2n. Now the question is whether this guy is equal to the geometric mean of 1 to 2n or not. So let's open this. So this guy is geometric mean of, this is what, a1, a2 up to an 1 over n, and then a1 n plus 1 up to product. Okay, and then geometric mean of two numbers is you multiply them and take the 1 over 2 power. So then this is a1 a2 a2n 1 over n 1 over 2, which is equal to a1 a2 a2n 1 over 2n, which is equal to geometric mean of 1 to 2n. So this is the proof for the case when n is a power of 2. Now let's say n is not a power of 2. So then what we do is we choose m greater than n to be the closest power of 2. Okay, so there is some m which is greater than n and which is the closest to n. Okay, Okay, so then since m is a power of 2, we already have proved that arithmetic mean of 1 to m, this is greater than equal to geometric mean of 1 to m. Okay, okay, so now let's open the right hand side. So this right hand side is equal to a1, a2, an plus 1 up to am to the power of 1 over m. Okay, this guy is, I'll just flip this inequality. So this guy is this. Okay, okay, so what Cauchy did very smartly was to choose those numbers. He said that up to an to am, they are all equal to the arithmetic mean of first n numbers, and he called it, and let's call it alpha. Okay, now my question is that if we have arithmetic mean of 1 to n is alpha, and all the numbers from an plus 1 to m are also alpha, then what is the arithmetic mean of 1 to m? So my conjecture is that this is also equal to alpha, but let's see. So then this is equal to a1 plus a2 plus an plus an plus 1 plus am divided by m. Okay, so then this sum is what? This sum is alpha times n, because the arithmetic mean of first n numbers is alpha, and all these are alphas. And how many alphas are there? M minus n divided by m. So this is equal to alpha. So this means, going back to our original inequality, then this guy is, when we say that this is less than 8m, so then this guy becomes alpha, and this guy becomes alpha to the power of m minus n. So let's go back to this situation again. Now we have a1, a2 up to an, then an plus 1 up to am to the power of 1 over m. This is less than alpha, and then we can say a1, a2 up to an to the power of 1 over m, and then alpha to the power of m minus n over m. This is less than alpha. Then we can say that a1, a2 up to an, this is less than alpha, 1 minus m minus n over m. This is equal to alpha, sorry, this is 1 over m, n over m. Now I can raise both sides to the power of m over n. So I will get a1, a2, an 1 over m to the power of m over n. This is equal to alpha, n over m to the power of m over n. So then this guy becomes a1, a2 up to an 1 over n. This is less than, sorry, this should be less than alpha. So then this means what? This means that geometric mean of 1 to n is less than the arithmetic mean of 1 to n. So this was a very smart proof by Cauchy. So hope it was easy to understand. The main trick is in induction. The main trick was that we applied induction for the case when n was a power of 2, and the other case we just use this result to and manipulate the results a little bit, manipulate the number a little bit to prove our final result. So this is it for the relationship between arithmetic and geometric mean and something about mathematical induction. Hope it was easy to understand and hope you liked the video. Thanks for watching.